Thank you very much. The title seems to be a little abstract, but I can promise that it will not. It is much easier than it seems. It is the title of our paper recently submitted to a mathematical journal. That's why it's the mathematical wording. So for the first slide, I usually use this for an introduction. So we are living in an AI era. So this will be about AI, the mathematics of AI. And this talk. So we live in the era of AI. I don't want to take too much time on the slide because everybody knows that. Some points, maybe the first is that when I gave this talk 1 year ago, then I wouldn't do in this wording. I mean, so last year the multimodal systems, it was a real breakthrough, and nowadays all of the specific tasks, text, code, image, speech, video recognition, and generation can be done by multimodal system. And there are other specific systems around as well. And the other thing is that nowadays, if you apply to a grant, for example, then it is to be explained if you not use AI and not if you use AI. So this is so common that everybody uses AI. Okay. The question is, what I want to address here is that how far can we go? To answer that question, let us reformulate it and ask another question that it's an old philosophical question actually, but can a machine be smarter than its creator? If we think about the traditional algorithms, then the answer is no, because in the traditional algorithms, we are who understand the problem itself. We write the code, and the machine just solves the code. So the machine is not smarter than us, just faster and okay, more effective, but not smarter. But the approach of the AI is the different thing, because in the AI we understand the understanding, and we write an understanding code, and the code itself, the machine will understand and solve the actual problem, and that's why in problem solving it can be smarter than us. But here is the big but, that understanding itself, it doesn't understand better than us, if you know what I mean. So the corollary is that to answer that, how far can we go, it depends on how well we do understand understanding itself. And finally, nowadays it's a very, very low effort is devoted to understanding. It is thought that understanding is well understood, and everybody works on the technology part, but I think it is a very crucial thing. And so let's go around this problem, and first let's overview what is our current picture of understanding. And this is I may say that the cognitive model of the present day AI systems, the present day understanding of understanding, it's a simple feed forward, I can say, action focused system. That means that we have a sensory information, we have a black box where the information is processed. Then it immediately goes to an action. We do some action which usually can be just returning the actual class of the incoming image, for example, or the next token in the large language models, but it can be a real action as well, like in case of robots or autonomous system. But this is the point. And actually, the learning or the training goes that the action is evaluated by some means, and then it leads to model improvement, and then it improves the information processing system. So this is the model of this present day AI system, the actual understanding of the understanding, the actual status of understanding of understanding. What are the consequences of that? First is that the point is that action directly comes from the input. There can be issues like randomization and things like that, but this is the main. So this is a feed-forward direct action focused system. As a consequence, there is no self-verification, no chance to control the quality of the answer. Of course, nowadays we are trying to reiterate the answers, so we try to somehow catch this point, but the system itself doesn't provide a good measure to control the quality of the answer. Next thing is also very interesting, that it lacks awareness of its knowledge boundaries, which means in everyday words that it doesn't know what it doesn't know, and it doesn't know what it knows. So that is so important, the prompting in large language models, because it doesn't know what it knows. So you have to dig out the knowledge, which is very deep and very, very comprehensive, but it is not, it is just answer to the prompt. And summarizing, it is an intuitive, unconscious, slow to learn, fast to act system, which resembles in human psychology or cognitive science. It's called System 1 by Daniel Kahneman. And mathematically, it is a function fitting. I've heard a lot of people saying that AI is nothing else, just function fitting. And indeed, this model is just function fitting. Okay, so this is the mathematics of the present day AI. Is this adequate? Is this good? Is it good? Why? If it is not, why not? The problem is in real life, I mean in biology, evolution, that too many types of situations can happen, can occur, especially in a 3D environment, and we cannot work out answer for each and every of the possible situations. We even cannot measure the quantity of the possible situations. There are infinitely large number of possible situations. We have not enough memory to store. We have not enough data to learn all of the situations, and that's why the living creatures developed a different type of cognitive system, where because we need a mental model that reacts to unknown situations reasonably. Maybe it's not very perfect, not very accurate, but reasonable. And that's the point where to the present day AI can fail miserably. So, and that means that in fact, the mental model we are needed, it must somehow represent the complete world, or at least that part which are relevant for us, which affect us. And in human psychology, this is called System 2. And in AI, there are a lot of attempts to do that, to attack this problem. Usually goes under the umbrella of representation learning, but other topics are taken as well. So let's a little bit overview what is going on there, and what is the mathematics between the System 2. So this is the cognitive model of System 2. And as you see, in between the info, I can't see the red dot even myself. So in between the information processing part and the action part, there comes an internal model, which represents the world. So actually, in this case, the sensory information after information processing updates the internal model of the world, and only after that there comes an action evaluation and model improvement. And this is not a function fitting problem, but what? So what is the mathematics behind System 2 and the world representation? And that's what we have addressed. This is the question that we try to answer in this. Actually, it's not a so all elements of this thing is known, probably is not put together, and it is not so common knowledge what is the mathematics behind this stuff. Let's use a simple physical approach to understand this math. So let us define the universe, big words, universe. Let's speak about the whole world. We define universe, observer, space and time, just as in physics we do. So this is not so important. Yeah. We use states in the world, which are called the possible configuration of the universe in the spatial instance, which leads to, contains all information to be able to predict the future. A very important point is that the observed world is smaller than the universe. We don't need to have, we don't need a full description of the universe. We don't have the means for that. So the single observer has finite observation processing capabilities. So it is not, cannot be done, but it is not necessary as well, because many details don't play a role for the agent's purpose, for example, for survival. For example, to describe the fate of a book, the position of the Mars is absolutely irrelevant. So we don't have to take it into account. And that means that, in fact, or objects or the objects of our thinking are not just states of the universe. These are collections of states. So a book, for example, a book is a collection of all kinds of states of the universe, containing the Mars at position 1 and the Mars at position 2, and all of the other irrelevant details are included in this subset. So actually, classes or objects are subsets of the universe, which collect all the irrelevant details. And then examples, as I've said, for example, a book is a collection of states where Mars is in different position, or a red pixel. That means that a collection of all images where that given pixel is red. But it is actually in language of states, it's a collection of states. The next thing is the context. To be more specific about what is a context. So if we have a concept, we can have different points of view. And for example, a book can be the world of books can be divided by in different parts by a bookshop, a collector, a reader, a mover. A bookshop for a bookshop, it is the price is important, the genre, or the popularity. For a collector, the issue time and things like that. So the first issue, the later one. For a reader, the content is important. For a mover, is it just the weight of the book is important, or the packability. Or the other question is that the dogs can be divided by their owner or by their breed. So all of the basic concepts can be divided in from different points of view, and these are called contexts. So if for mathematically, the context is actually the partition of the underlying class. That means that we divide it as a complete union and of subsets. Like here, you can see the books can be divided fully by the name of the author. For a very short thing, I don't want to spend too much thing here. In physics, there are different contexts as well. For example, if we think about a table, we can analyze it according to these mechanical properties or the matter content or things like that. But in physics, usually we associate the context by the scale. And we think or tacitly think that at each scale there is a single context, and it is usually not true for an everyday life. In a given scale, there can be a very lot of context, and this is where the AI is so important. So that just keeps it. And now we can define operations on context. So these are just partitions of elementary of the underlying set. We can portion it, so then melt together several parts, or refine it. subdivide some subparts, some subsets of the context. Like if you have apple varieties like Jonathan Gala and things like that, and apple is a coarsening for the apple, the species, I mean the apple variety is a refining. Or individual images, which the coarsening is that which we speak only the cat, dog, or other images and things like that. So these define the algebraic relation of the context. So it is not a numerical solution. It is the algebraic relation of the context. How can we represent the context? There are several ways. The direct representation is that if we have a subdivision of the underlying set, all classes of the context is treated separately. This is called one-hot encoding or system one. So this is what in usual AI, which gives back a class or gives back classes, use this direct representation. But there are other possibilities which we use in everyday life very frequently. For example, the global coordinates. That means that we define several simple contexts, and we use the intersection of this context of this subset. For example, when we speak about a vector space, we can be divided by r to the n. So we divide it by n simple subcontexts. Or as you see here, instead of defining the dogs or the cats by itself, we can define several binary subcontexts, and then we can, with multiple binary subcontexts, we can go around and define the realm of dogs themselves. Okay, but actually, there is another one when you use local coordinates. That means that we start with a simple context, a simple partition with few subsets, and then subdivide each classes, each subset independently of each other. And this defines a refinement tree. It's a tree structure, like in taxonomy, for example, or the 20 questions in English. It's called Barkóba in Hungarian. Okay, just some minutes. Yeah. And interestingly, there is in information theory a theory that there is an optimal coding, and it is called Kuffman coding. I don't show the I don't want to go into details. If there is a question, I can show you. But the point is that the local coordinates implement very nicely or very closely the optimal coding of the information theory result. And last, okay, I don't also this was the algebraic part. And yeah, okay, this refinement tree sometimes is called knowledge graph. This is the concept in the title. So for numerical representation, what we have to do is that we have to find the numerical correspondence of the classes of the context, which is called features, which are functions that are constant on the classes of the context. So it is a class valued functions because it inverse image then provides an induced context, which is a subcontext of the original one. Okay, other names is conserved quantities or measurable functions. This so for physicists or for everyday life, the conserved quantities is the most important notion here. So that means that, and this will be my last slide. So how we have to approach system to build a system to train or teach a system to is that first we have to collect the data and measurements, and it's okay. Then we have to single out the context. So we have to ask the proper questions. For example, we have to want to do sound recognition, image recognition, things like that. And then we have to try to find context valued class valued function, concert quantities. So quantities, functions of the original space, which are constant on the classes of the context. But there is not such an easy way to find them, like in the backpropagation, for example. There are some tricks to do that. For example, find sparse representations, or what we've done in the living world, that they observe which coordinates are interdependent. And then for that, causality can be used, and the Hep's rule of biology is just implementing these things. Okay, so I have no time left. So this is my last slide, and thank you for your attention.
Thank you very much, Tony. So the topic was super interesting. I would have thousands of questions, but we have time only for one short. So if anyone would like to, Laci, you were the.
Thank you very much. So considering agentic AI, you can design a hierarchy of agents to execute some task. Would you consider this system a system 2?
I think it's not a system 2 by design. So nowadays, what we do is that we try to get out from the system, the environment of system 1s, and but I sometimes give this example that if we want to create a flying machine, and we created a wolf machine, a machine wolf, then we can try to pretend that the wolf can fly, because it can leap a lot, or it can be leap down in a steep place, and then it spends a lot of time in the air, but it doesn't fly. So to build a flying machine, we have to understand flying. This is the point. Yes, a lot of people. So this is the direction people try to do. For example, when the reasoning models is introduced, try to control itself, but there is no reality. There is no model of reality, and it's very ad hoc. All of this attempt. There are attempts. There are systematic approaches, but it is nowadays it's not a mainstream. It's a second rank.